So here we are, and suppose the position of the combined mass when the string is horizontal, let me call that position to be C here. So what are the forces acting on the combined mass as it's traveling? There is a force of tension exerted by the string in the radial inward direction, that is from C towards O, and also the force of gravity that is acting vertically downwards. And this is the force of gravity, of course, twice m the mass into g, and this is the force of tension responsible for the centripetal acceleration of this combined mass. I can show that radial acceleration also by this red arrow. This is, I'm calling it radial acceleration, that is AR. So equation of motion of this combined mass in the radial direction, that is horizontal in this case, we could write down that in radial direction the net force Fr is the force of tension. The gravity force has got no contribution radial direction because this force is vertically downwards and the radial direction in this case is horizontal. Therefore, the tension force is the only force accounting for any possible centripetal acceleration. The mass of the combined body is twice m and the radial acceleration is AR, and this is twice m into AR is given by, suppose the speed of this combined mass at position C, I'm calling it to be V dash. So it is V dash square divided by the radius of this circle, that is equal to the string's length, capital L here. So that is the equation of motion in radial direction. Since they have said at horizontal position the tension of the string becomes 0, therefore we are getting that since tension is 0 in horizontal position, it follows therefore from the previous line equation here that the speed V dash of the combined mass at position C must also be equal to 0. That is the result we are getting from the expression. And once we get the speed at point C is 0, we can apply the conservation principle of mechanical energy between the points B and C for this combined mass plus earth system. So I'm going to apply here the mechanical energy conservation principle. Why can we apply that? For the system comprised of the earth and this combined mass that is made up of this object and the stone, the only external force acting on the system is the force of tension. But since the tension force is always perpendicular to the displacement of this combined mass in the circular motion, the force of tension does not do any work on my system, and therefore mechanical energy for this earth plus combined mass system must remain conserved between the points B and C. B is the lowest position of this combined mass in a circular path. Let me assign a value of 0 to the potential energy of the system at position B, and therefore we might write down that between the points B and C, mechanical energy at B must be equal to mechanical energy at C. What is mechanical energy at the lowest position B? The kinetic energy that is given by half into the mass of the combined body, that is twice m, the speed at the lowest position B that was already found to be capital V, 2.5 meter per second. So I'm writing this V only here, that is V square. This is kinetic energy of the system at point B. Potential energy is assigned a value of 0 at this position B. So that is the left hand side. Go to the right hand side. At position C, the kinetic energy becomes 0 because V dash is already found out to be 0 at this position, previous step. The potential energy now becomes mgh. Mass is twice m for this combined body. G is free fall acceleration, and the height of the point C above the point B is equal to the length of the string, that is capital L, isn't it? So comparing these two sides, we can see mass of this combined body is cancelling out, and we get from here, allow me to write somewhere here, I get the value of L is coming out to be V square divided by 2G. The value of V was already found to be 2.5 meter per second. So this is 2.5 meter per second squared divided by twice the free fall acceleration, 9.8 meter per second square. Complete the calculation and show that the value of L is coming out to be about 0.32. I am getting 0.32 meter into significant figures. And this is the answer of part B of the question. You have got that if the string becomes without tension at horizontal position, then the length of the string must be about 0.32 meter. And this is the complete answer of this question.
Hello students, you got a glimpse of our video lessons through this small lecture. We have hundreds of lectures like this one covering various topics of advanced school level and intermediate physics in our website. They are exhaustive and often accompanied by elaborate diagrams to make concepts even clearer. They are taught with passion and sometimes with a bit of fun. So, at the end of the lesson, you have a commanding grip on the subject and you are ready for the board and competitive exams. Subscribe at physicsacademyonline.com to access video lectures of highest standard on various topics of physics.